You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Serverless computing represents a major evolution in how applications are designed and deployed. Instead of provisioning and managing servers, organizations supply only their code, while the provider manages the runtime environment. This abstraction allows developers to focus purely on functionality, with infrastructure concerns like scaling, patching, and capacity handled automatically. Yet while the operational burden shifts to the provider, security responsibilities do not disappear, they change form. The control surface in serverless computing spans events that trigger functions, execution contexts where code runs, and governance mechanisms that oversee access and policies. Without careful management, the speed and agility of serverless platforms can magnify risks, such as privilege misuse or data exfiltration. By understanding how events flow into functions, how execution is constrained, and how governance shapes roles and access, professionals can harness the power of serverless without sacrificing security or accountability. At the core of serverless computing is the idea of event-driven execution, where functions are invoked in response to specific triggers. This is most often implemented through function as a service or FIND-RIFAAS, which allows short-lived code snippets to run when events occur. Examples include a file upload to storage triggering an image processing function or an HTTP request invoking an authentication routine. These functions scale automatically, running in parallel when demand increases and shut down when idle, minimizing cost. Security considerations emerge because these functions often touch sensitive data or act on behalf of privileged services. Unlike long-lived servers, serverless functions may run only for seconds, making logging, monitoring, and role assignment more challenging. Understanding serverless begins with recognizing that the absence of visible infrastructure does not mean the absence of risk. Instead, it requires shifting focus to the boundaries where events meet execution. Function as a service, or FIND-SASU, deserves particular attention because it defines the operational model for most serverless platforms. Functions are designed to be short-lived, stateless, and event-driven. They scale horizontally, with multiple instances executing simultaneously when event volumes surge. This elasticity makes them ideal for unpredictable workloads, but it also introduces challenges. For example, a poorly designed function could inadvertently overwhelm downstream systems during a spike in invocations. From a security perspective, FAAS requires strict scoping of permissions and careful design to avoid side effects from retries or concurrency. Functions must also be small and targeted, as bloated code increases attack surfaces and slows execution. By thinking of FAAS as code on demand, professionals see both the advantages and the responsibilities. It delivers flexibility but requires precision in managing how code interacts with data, resources, and external systems. Event sources form the lifeblood of serverless systems, supplying the triggers that determine when and why functions run. These sources can include HTTP requests arriving through APIs, messages placed on queues, records in data streams, scheduled tasks, or notifications from storage services. Each type of event brings unique risks and design considerations. For instance, HTTP endpoints must guard against injection attacks, while storage events must ensure that only authorized users can trigger sensitive workflows. The diversity of event sources makes it essential to implement validation and access controls at the entry point, preventing malicious or malformed events from propagating downstream. Without these safeguards, serverless platforms risk becoming too permissive, where any event legitimate or hostile can trigger code execution. Recognizing the variety of event sources helps administrators and developers apply appropriate controls tailored to each pathway. Invocation models determine how events are processed once they reach the serverless platform. Synchronous invocations return results directly to the caller, as in an API response, while asynchronous invocations queue events for later processing. Asynchronous models often include retry semantics, where failed executions are retried automatically. While retries improve resilience, they can also create duplication risks if not managed carefully. For example, a payment processing function might be retried multiple times, resulting in double charges if idempotency is not enforced. Synchronous models, by contrast, require careful timeout management to prevent clients from waiting indefinitely. Each invocation model affects not only performance but also security, as retries and queues expand the need for monitoring and control. Designing with invocation models in mind ensures that functions behave predictably, with clear handling for both success and failure conditions. Concurrency management addresses the challenge of balancing elasticity with stability and cost. Serverless platforms allow functions to execute in parallel, but unlimited concurrency can overwhelm dependent systems or lead to runaway expenses. Throttling and burst limits provide safeguards, ensuring that invocations remain within safe thresholds. For example, a function triggered by a message queue may be limited to processing a certain number of messages per second to avoid saturating a downstream database. Concurrency controls also protect against denial of service attacks, where attackers flood event sources to consume resources. By defining explicit concurrency limits, organizations not only control cost but also create predictability in how their systems respond to load. Concurrency management illustrates how operational controls and security overlap in serverless environments, ensuring that scalability serves business needs without introducing instability or uncontrolled risk. Cold start behavior introduces unique operational concerns in serverless platforms. When a function is invoked after a period of inactivity, the provider must initialize a runtime environment, causing a delay known as a cold start. While this affects user experience, it also influences security considerations. Initialization processes may load environment variables, establish connections, or retrieve secrets. If these steps are not managed properly, sensitive data could be mishandled or exposed in logs. Cold starts also shape timeout settings and retry logic, as slow initialization may cause functions to appear unresponsive. Some providers offer warm options to reduce latency, but these come with trade-offs in cost and availability. Understanding cold starts helps administrators tune both performance and governance, ensuring that initialization routines are efficient, secure, and resilient against misuse. Identity and access management roles form one of the most critical security controls in serverless environments. Each function executes with an identity that determines what resources it can access. Following least privilege principles, these roles must be narrowly scoped to grant only the permissions required. For example, an image processing function might need access to a storage bucket, but not to a database. Misconfigured roles are a common source of breaches, as overly broad permissions allow attackers who compromise a function to escalate privileges. Auditing role policies and monitoring usage helps detect excessive or unused permissions, providing opportunities for refinement. IAM roles transform security from an afterthought into an enabler, ensuring that functions act only within their defined boundaries and that misuse is both difficult and detectable. Resource policies complement IAM roles by defining who can invoke, publish, or consume events. While roles govern what functions can do, resource policies govern who or what can interact with event sources and targets. For example, a resource policy might restrict which identities can publish messages to a queue or invoke a sensitive function. Without these controls, attackers could trigger functions directly, bypassing intended workflows. Resource policies thus serve as guardrails, narrowing the circle of trust around critical event pathways. They also provide defense in depth. Even if a function's permissions are scoped correctly, unauthorized invocation can still cause disruption if resource policies are left open. By combining IAM and resource policies, organizations create layered controls that secure both action and interaction within serverless platforms. Network integration options determine how functions connect to other resources, shaping both accessibility and exposure. Functions may be invoked through public endpoints, allowing global reach, or through private service links that restrict access to internal networks. Virtual private cloud attachments extend control further by placing functions within private subnets, where security groups and routing policies apply. Each option reflects a trade-off between accessibility and security. Public endpoints enable convenience but expose functions to internet traffic, requiring robust filtering and authentication. Private integrations reduce attack surface but may limit flexibility. For example, attaching a function to a VPC allows it to access internal databases securely, but adds network complexity. Choosing the right integration model requires aligning technical design with security posture, ensuring that functions communicate only in ways that are both necessary and controlled. Secrets handling in serverless environments requires particular discipline because functions often need credentials or keys to interact with other services. Storing these secrets as plain environment variables or hard-coding them into code is unsafe, as they can be exposed in logs or stolen during compromise. Secure approaches use encrypted environment variables or vault integrations, retrieving secrets at runtime with strict auditing. Access to secrets should be logged, and their rotation must be automated to prevent long-lived vulnerabilities. For example, a function accessing a database might retrieve its credentials from a centralized vault at invocation, receiving a short-lived token instead of a static password. Secrets handling illustrates the balance of usability and security. Developers need seamless access, but organizations must enforce rigorous lifecycle controls. Done correctly, secrets handling transforms a common weakness into a controlled and auditable process. Ephemeral storage and temporary directories present another often overlooked risk in serverless functions. During execution, functions may use local storage for caching or intermediate data. While convenient, this storage persists only for the lifetime of the execution environment and may inadvertently retain sensitive data longer than intended. If functions reuse environments, residual data could be exposed to subsequent invocations. To prevent this, organizations must enforce lifecycle hygiene, ensuring that temporary storage is sanitized after use. Encryption adds further protection, ensuring that even if data lingers, it remains inaccessible. For example, a function processing customer records should explicitly delete temporary files and avoid leaving unencrypted copies in ephemeral storage. By treating temporary storage as a security concern, administrators prevent data leakage and reinforce the principle that serverless functions should remain stateless and isolated by design. Observability baselines transform the ephemeral nature of serverless functions into something measurable and accountable. Structured logs capture execution details, metrics track performance indicators, and distributed traces provide end-to-end visibility across event flows. Correlating these artifacts to request identifiers allows administrators to follow individual transactions through the system. For example, tracing an API request through multiple functions provides insight into latency bottlenecks or failure points. Observability also supports security, as anomalies in logs or metrics may indicate misuse or attack. Without observability, serverless systems become opaque, with short-lived functions leaving little forensic trail. With it, they become transparent, enabling both operational optimization and security assurance. Establishing observability as a baseline ensures that monitoring is not optional but integral, allowing organizations to balance agility with accountability in serverless environments. Idempotency keys and safe retry designs address the reality that serverless platforms often deliver events with at least once semantics. This means that functions may process the same event multiple times, especially when retries occur after transient failures. Without safeguards, this can create duplicate side effects, such as double charging a customer or reprocessing an order. Idempotency keys uniquely identify requests, allowing functions to detect and discard duplicates. Safe retry designs ensure that operations can be repeated without harmful consequences. For example, inserting a record into a database might check for an existing identifier before committing. These patterns are as much about security as reliability. preventing attackers from exploiting retries to amplify impact. By designing for idempotency, organizations create resilient functions that behave predictably even under the imperfect delivery guarantees of distributed systems. Package management becomes particularly important in serverless because functions are often small but dependency-heavy. A single function may import dozens of libraries, each carrying potential vulnerabilities. Governance over package management ensures that dependencies come from trusted sources, versions are pinned, and unapproved software is excluded. Provenance tracking confirms that packages have not been tampered with, while minimizing code size reduces attack surface and cold start latency. For example, trimming unused dependencies not only improves performance, but also eliminates unnecessary exposure to flaws. Package management in serverless reflects the broader theme of software supply chain security. Trust is not just about code you write, but also about the components you inherit. By treating dependencies as carefully as proprietary code, organizations reduce the likelihood of hidden vulnerabilities entering execution environments. Provider patch responsibility is a defining characteristic of serverless, where the infrastructure and runtimes are managed by the provider. This relieves customers of patching operating systems or hypervisors but does not eliminate their responsibilities. Tenants remain accountable for the security of application logic, dependencies, and configuration. For example, while the provider ensures that the runtime environment is up to date, it is the customer's job to update vulnerable libraries in their code. This shared responsibility model can create blind spots if misunderstood, with customers assuming providers handle more than they do. Clarity on division of responsibility is essential, as neglecting tenant-side patching undermines the security of the entire application. Serverless platforms succeed when both provider and customer fulfill their roles, creating a balanced model where managed services provide efficiency without eroding accountability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Threat modeling for serverless systems begins with recognizing the unique risks introduced by event-driven execution. Unlike traditional servers that expose a few well-defined interfaces, serverless functions may be triggered by a wide variety of event sources, each with its own attack vectors. Event injection is a key concern, where malicious input is crafted to exploit logic flaws in functions. Deserialization flaws can occur when untrusted data is converted into objects without proper validation, potentially enabling code execution. Execution role abuse represents another risk, as compromised functions may misuse their assigned privileges to access sensitive resources. By systematically analyzing how events enter the system, how data is processed, and how roles are scoped, organizations can anticipate potential attacks before they occur. Threat modeling thus becomes a proactive exercise, helping teams align security controls with the realities of serverless architectures. Inbound validation provides the first defensive layer for serverless functions, ensuring that only properly formed and authorized requests are processed. At API entry points, schema validation enforces the structure of incoming data, rejecting malformed payloads before they reach application logic. Content limits prevent oversized requests from overwhelming resources, while authentication ensures that only trusted parties can invoke functions. For example, an API gateway can validate JSON schemas, enforce rate limits, and require tokens before forwarding requests to functions. This reduces the chance of injection attacks, resource exhaustion, or unauthorized access. Inbound validation is not just about protecting code, but also about preserving stability, ensuring that event streams remain predictable and controlled. Without these checks, functions become exposed to the noise and malice of the open internet, making them vulnerable to both accidental misuse and deliberate exploitation. Outbound egress controls are equally important, as they restrict what destination serverless functions can communicate with. Without constraints, a compromised function could exfiltrate data to an attacker-controlled endpoint or participate in command and control networks. Egress policies define approved destinations, ensuring that functions only connect to trusted services. For example, A function processing payments may be limited to contacting the payment processor's API and nothing else. Restricting egress reduces the potential impact of compromise and helps detect anomalies, as attempts to connect to unauthorized destinations can trigger alerts. In environments where compliance requires data locality, egress controls also prevent accidental transfers across regions or jurisdictions. Together with inbound validation, egress restrictions create a controlled envelope around functions, ensuring that communication flows remain both purposeful and auditable. Data protection requirements in serverless environments apply the familiar principles of encryption in transit and at rest, but with some unique considerations. Transport layer security, or TLS, must be enforced for all communication between functions, event sources, and external services. At rest, artifacts such as deployment packages, logs, and temporary files must be encrypted to prevent exposure. Providers often offer built-in encryption for storage, but customers must configure and monitor it properly. Keys must be managed carefully, ensuring rotation and secure storage in centralized services. For example, a function writing to a storage bucket should do so with enforced server-side encryption, using customer-managed keys for added assurance. Data protection ensures that even if communication is intercepted or storage media is compromised, sensitive information remains secure. These controls transform confidentiality from a best practice into a verifiable, enforceable standard in serverless platforms. Dependency risk management addresses the fact that most serverless functions rely heavily on third-party libraries. These dependencies may contain vulnerabilities or license obligations that introduce hidden risks. A software bill of materials, or SBOM, provides visibility into which components are used, while vulnerability scanning identifies flaws. Signature verification ensures that packages have not been tampered with. For example, if a new vulnerability is disclosed in a widely used library, an SBOM allows administrators to immediately identify affected functions. Without this visibility, organizations may be running code with unknown exposures. Managing dependency risk is about more than patching. It is about ensuring that every component can be traced, validated, and justified. In the serverless model, where functions are small but dependency-heavy, governance over third-party code is indispensable for maintaining both security and compliance. Code signing policies extend trust into the deployment pipeline, ensuring that only approved packages can be executed. By requiring signatures on all deployment artifacts, organizations prevent unverified or tampered code from entering execution environments. Code signing attests both provenance and integrity, providing evidence that the function was built through authorized processes. For example, a signed deployment artifact ensures that what runs in production matches what was approved in testing, without unauthorized modifications. Verification at deployment blocks unsigned or improperly signed code, enforcing discipline. In practice, code signing transforms the deployment process into a chain of trust, where every stage build, test, release is validated. This reduces the risk of insider threats, supply chain compromises, or accidental misconfigurations, leading to insecure code running in production. For serverless environments, where code can be deployed rapidly, code signing serves as a critical gatekeeper. Resource constraints such as timeouts, memory limits, and CPU settings provide both operational and security benefits. By bounding resource usage, organizations prevent functions from consuming more than intended, which could disrupt systems or inflate costs. Timeouts ensure that functions do not run indefinitely, which could amplify denial-of-service attacks or hang in faulty loops. Memory and CPU limits prevent a single function from exhausting host resources, protecting other tenants in multi-tenant environments. For example, setting a timeout of 5 seconds on an API function prevents attackers from forcing prolonged execution through crafted inputs. These constraints align with the principle of least privilege, applied not to permissions but to resources. By enforcing boundaries, organizations reduce opportunities for abuse, create predictability, and protect overall platform stability. Dead letter queues and retry policies provide structured ways of handling failures in serverless systems. Instead of discarding failed events, dead letter queues capture them for further investigation, preserving context for debugging and forensics. Retry policies define how and when functions reattempt processing, balancing resilience against the risk of duplicate execution. For example, an event might be retried 3 times before being routed to a dead letter queue for manual review. This ensures that transient errors do not result in data loss while preventing infinite loops. Dead letter queues also support compliance by maintaining evidence of failures and how they were handled. By embedding these practices, organizations turn failures into opportunities for learning and accountability, ensuring that errors are contained, analyzed, and resolved systematically rather than lost in the noise of transient execution. Multi-tenant isolation is a fundamental design requirement of serverless platforms, as providers host functions from many customers on shared infrastructure. Providers use sandboxing techniques to isolate workloads, but customers must complement these protections with their own controls. Least privilege roles ensure that functions cannot overreach their intended authority, while scoping event sources prevents cross-tenant contamination. For example, even if the provider prevents one tenant's code from accessing another's memory, misconfigured permissions could still allow unauthorized access to shared storage. Isolation is therefore a shared responsibility, combining provider-level guarantees with customer-level diligence. Recognizing the limits of provider assurances helps customers design defensible architectures that assume potential weaknesses and enforce boundaries rigorously. Multi-tenant isolation ensures that one tenant's vulnerabilities do not cascade into systemic risks across the platform. Long-running workloads present a challenge in serverless environments, which are designed for short-lived execution. To stay within execution limits, functions must be re-architected using event chaining, step orchestration, or durable function frameworks. Event chaining breaks tasks into smaller steps, each triggered by the output of the previous one. Step orchestration coordinates these tasks through managed workflows, ensuring sequencing and error handling. Durable functions extend state management across multiple executions. For example, processing a large video file may be split into smaller chunks processed sequentially. These approaches align workload design with the constraints of serverless, preventing functions from exceeding timeouts or resource limits. From a security standpoint, they also reduce exposure by keeping executions brief and focused. By embracing patterns for long-running tasks, organizations avoid misusing serverless while still achieving their operational goals. Private endpoint exposure and mutual transport layer security provide defenses for service-to-service communication within serverless systems. Instead of exposing functions through public endpoints, private endpoints restrict access to internal networks, reducing attack surface. Mutual TLS strengthens this further by requiring both client and server to authenticate each other, ensuring that only authorized services communicate. For example, a function may only accept connections from a specific internal API gateway, with both sides presenting certificates. This prevents impersonation and man-in-the-middle attacks, ensuring confidentiality and integrity. Internal meshes built on MTLS create secure fabrics for communication, aligning with zero-trust principles. By minimizing public exposure and enforcing authenticated connections, organizations protect the often overlooked internal pathways that link serverless functions together into cohesive applications. Cost governance in serverless is both a financial and security control, as uncontrolled invocations can signal abuse or attack. Tracking metrics such as invocation count, execution duration, and egress volumes allows organizations to spot anomalies, such as sudden surges that may indicate denial of service attempts or misconfigured loops. Budgets and alerts act as guardrails, preventing runaway costs that could cripple operations. For example, an unexpected spike in outbound data transfer costs might reveal attempted data exfiltration. Cost metrics complement technical telemetry, providing another lens through which to monitor system health. In serverless, where charges are directly tied to usage, financial governance is inseparable from operational discipline. By aligning budgets with security monitoring, organizations transform cost tracking into an early warning system for both financial and technical anomalies. Compliance evidence ensures that serverless environments remain auditable and defensible under scrutiny. This includes deployment manifests that show how functions were configured, role policies that define permissions, logs that capture execution history, and test results that validate controls. By mapping these artifacts to frameworks such as SOC 2 or ISO 27001, organizations demonstrate adherence to industry standards. Evidence generation should be automated where possible, embedding compliance into the same pipelines that manage deployments and monitoring. For example, every function release might automatically generate a compliance report showing role assignments, code signatures, and test outcomes. This reduces manual burden while increasing consistency. Compliance evidence is not just for auditors. It also reassures stakeholders that the serverless environment is being managed responsibly, with security integrated into every stage of the lifecycle. Incident response in serverless environments requires adapting traditional playbooks to ephemeral and event-driven contexts. Evidence sources include logs, distributed traces, and dead letter queues, all of which must be preserved before execution contexts vanish. Token revocation becomes critical, as compromised identities may persist across invocations. Investigating suspicious concurrency patterns can reveal abuse, such as attackers triggering excessive parallel executions to cause disruption. Incident responders must be prepared to work with both provider tools and customer telemetry, acknowledging the shared responsibility model. For example, while the provider may handle infrastructure-level forensics, the customer must analyze function logic and dependency vulnerabilities. Effective incident response ensures that even in short-lived, rapidly scaling environments, compromises are detected, contained, and remediated quickly, minimizing both technical and business impact. Anti-patterns in serverless design illustrate what not to do. Offering cautionary lessons. Granting wildcard permissions in IAM roles creates overbroad authority, enabling attackers to exploit compromised functions. Hard-coding secrets into code or environment variables creates static vulnerabilities that may be exposed. Allowing broad internet egress from functions increases the chance of data exfiltration and unauthorized communication. These practices undermine the security model of serverless, transforming its strengths into liabilities. Recognizing and avoiding anti-patterns is as important as adopting best practices, as mistakes are often amplified in elastic environments. For example, a single function with wildcard permissions may become the pivot point for a large-scale breach. By identifying anti-patterns early, organizations prevent avoidable risks and embed discipline into their development culture. In conclusion, serverless security depends on disciplined roles, validated events, controlled egress, and verified packages working in harmony. Roles ensure that functions act only within their intended authority. Event validation blocks malicious or malformed inputs at the door. Egress controls prevent unintended communication, protecting against exfiltration. Verified packages and signed code ensure that only trusted artifacts enter execution. Supporting practices like observability, incident response, and compliance evidence make these controls auditable and actionable. The result is a serverless environment that balances agility with assurance, delivering both the innovation organizations seek and the accountability regulators and stakeholders demand. For professionals, mastering serverless security means seeing beyond the abstraction, recognizing the control points that remain, and applying them rigorously to build secure, resilient, and transparent systems. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.